All right, so today we're picking up where we left off with using equilibrium constants in equations. And I did want to review actually this idea for what equilibrium is. So equilibrium is not a static thing, it's dynamic. So they're dynamic equilibriums. This was like all the way at the beginning. And it's where the reaction rate of the forward reaction is equal to the reaction rate of the reverse reaction. So we have as many products being made as we have products turning back into reactants. So they're flowing back and forth. So the concentrations of products and reactants, if you were to take a snapshot at any point, would be the same. So when you reach that point of equilibrium, dynamic equilibrium, you can calculate or really put together an equilibrium constant, right? Because if the concentrations stay the same for a reaction at equilibrium, then we can use the ratio of those concentrations of reactants to products to determine what that point would be for any reaction. And then for future reactions, you could say, well, if I add this much of, if we have an initial amount of hydrogen and iodine for this reaction, how much hydroiodic acid will we make at the end of that reaction? And how much hydrogen, how much iodine will we have left over that did not react? And then you can do that for any of these different scenarios. The ratio will be the same. So this also gives us a convenient way to calculate these things. So we can calculate KEQ. Remember that when we're putting together these equilibrium expressions or equations, we only include gases and aqueous compounds because solids and liquids don't change because there's so much of them with respect to the gas or the liquid. So you put these together, and if we know what the concentrations of the reactants and products are at equilibrium, we can calculate what that ratio is. And if we have the equilibrium constant and it depends on how many things there are. If we have the equilibrium constant and then the concentrations of everything at equilibrium except for one species, we can use those numbers to calculate that species. So in this case, we had the COF2. We also had carbon tetrafluoride. And we wanted to figure out the concentration of carbon dioxide gas at the end of this reaction. So we put together our equilibrium expression first. So CO2 and carbon tetrafluoride are our products, so they go on top. And then COF2, I'm trying to think of what the name of that is. But COF2 here is our reactant, so it goes on the bottom. And then we raise the concentration of anything to its exponent. So there's a 2 COF2 here, so we square the concentration of COF2. Then we can plug in all of the numbers that we were given and solve for the concentration of carbon dioxide. Alrighty. So it leads us right into another problem. So if in an equilibrium mixture, the concentration of I2 is 0.10 molar. What is the equilibrium concentration of iodine? Or just I? So the first step in any of these problems is going to be to write out the equilibrium expression. So we say KEQ is equal to, move that to the side. KEQ is going to be equal to the concentration of our products multiplied together, raised to the exponent of their coefficient. So here our product is is 2I, not to be confused with I2. So it's concentration of I squared. And then our reactant, since we only have one, is going to be the concentration of I subscript 2. So now we can take our equilibrium constant, plug that in for KEQ. So 0.011 is equal to, and we have the concentration of I2, so we can leave I squared there as our unknown, and the concentration of I2 will be 0.10 molar. So if we multiply both sides by 0.10 molar, so 0.1 times 0.011, we'll get 0.0011 equals I squared. So to get I instead of I squared, we need to take the square root of everything. So we'll do the square root of 0.0011, the square root of I2, or of I squared. And so 0.011 squared, not squared, square root of the heck. Calculator is not behaving. There we go. This is going to be 0.033 molar equals I. There's another way you can do this. It means the same thing, but it's a little easier to see as a formula. So taking the square root of something is the same thing as raising it to the 0.5 power or the 1/2 power. So we could also do this the same way and say that this is 0.0011 raised to the 1/2. So then this is going to be I squared raised to the 1/2. What's convenient about this is you can see that it's 1/2. So if you needed the third root of something, because one of those things had a 3 as its coefficient, you just raise it to the 1/3, or the 1/4, or the 1/13, which might happen. Rather than trying to figure out on your calculator how to do the 13th root. Okay. So Le Chatelier's principle is kind of a rule of, well, is it more than a rule of thumb? It's more than a rule of thumb, I guess. It's the idea, though, that when a chemical system at equilibrium is disturbed, that chemical system will readjust to minimize the disturbance. So you can think of the system at equilibrium fights back when disturbed. So if we had a reaction like this, I2 equals 2I. If we add more I2, or add more I, increase that concentration, this reaction will shift to the left. So the reaction will shift, and I should draw these arrows like this. Will shift to the left to try and reduce that concentration of iodine, or the I. If we do the opposite and we add to the left side of the reaction, same reaction here, and we add more I2 instead, that'll cause the reaction to shift to the right. And then if we think about this at a sort of fundamental level of what's happening, remember that reactions happen when molecules, well, this one's not a great example because there's only one product and one reactant. But you have to have molecules colliding or in conditions that will have enough energy for them to react. So if two molecules are colliding, where they need to have enough energy, which could come from them hitting faster, or by pure statistics, by having a lot of reactions or a lot of interactions. So if you're increasing the concentration of I, you have more I molecules flying around, more of them colliding, and more of them reacting to form I2. So that's going to increase the rate of the reverse reaction, while the rate of the forward reaction remains the same. So if that rate of the reverse speeds up, then we'll have more I2 formed, that's the reaction shifting left, until those rates become the same again. So we had this analogy of Middle Earth and Narnia, and so everybody moved over to Middle Earth, and they had this equilibrium. So let's say that population is added to Middle Earth. Let's say, this will tell you how big of a nerd I am, and maybe this won't resonate with anybody, but Sauron raises a whole bunch of more Uruk-hai for his army. So he raises this army, right? Now he's got this huge army that adds to the population. They need homes, they have families, whatever. So people will start to move out of Middle Earth back to Narnia because they say, well, for one thing, maybe they don't want to be around the war, but also that there's more people here. Like we can move out, we can go over there where it's more spacious. Imagine the people of Middle Earth like their large yards. Anyway, so what would happen though if, like in Lord of the Rings, this huge war happens and the population of Middle Earth is reduced? So suddenly there are a lot less people in Middle Earth than there were before the war. Where are people going to move? They're going to move to Middle Earth, right? They're going to move to where their space is. So reactions are kind of like this, but more related to the rate of equilibrium than the housing market, or the rate of the reverse or rate of reactions rather than the housing market. So the reaction shifts, when product is added, so product, that's this side. When product is added when a reaction's at equilibrium, our rate of the reverse reaction increases, because now we have more particles than we did before, all colliding, so we have more collisions. So that rate shifts, rate increases, and so the concentration of the reactants will go up. If that concentration increases, then that rate will increase, and so you'll reach this point in the middle again, where now we've got higher concentrations of both products and reactants, but they sort of come up together until those rates are the same again. So increase in concentration increases the rate and causes the reaction to shift. I'm just going to skip that slide. So if we add reactant, because it's a static image, it's just, I don't think it does a good job. So adding reactant causes, again, now we're adding this, the reactant side. So if we add reactant, that's going to increase the rate of the forward reaction. That's our forward reaction. And so our reaction shifts to the right until there's enough product that the reaction rate of the reverse reaction is equal to the forward reaction again. Again, those static images don't do much. So if a chemical system is at equilibrium, which everything we're doing right now is at equilibrium, increasing the concentration breaks that equilibrium. And if we increase the concentration of one or more reactants, causes the reaction shift to the left. Increasing the concentration of one or more of the products, adding reactants shifts it to the right, adding products shifts it to the left. So the system be like increasing concentration of products, slide to the left. increasing the product concentration of the reactants, slide to the right. Everybody clap your hands. Okay, so now we can use the Mentimeter. So for this following reaction in a chemical equilibrium, what happens if we add more bromine, Br2? Are we adding more product or are we adding more reactant? We're adding more of the product. So which way does the reaction shift? To the left. To the reactants. So if we add BrNO, which way does the reaction shift? If we add more, so it's a reactant, so if we add more reactant, it'll shift to the right. Yep. So we'll have more products. What happens if we remove some bromine? So if we remove some of our product, which way will the react? Was it? It'll still shift. It'll shift to the right. So remember, if we remove bromine, we decrease the concentration of bromine, which means that the rate of the reverse reaction slows down. Doesn't change the rate of the forward reaction, but now it's faster than the reverse reaction, so it'll fill in that hole. So it'll shift to the right. So basically, if you add more, it will shift away from what you add. If you remove something, it'll shift towards what you remove. So we can add a level of complexity here with gases. So if we change the volume of a gas, that changes the pressure. And if you remember, the pressure of the gas is the concentration of the gas. So those two things are the same. So if the pressure of a gas decreases, the concentration of that gas decreases. So if we decrease volume, that's like taking a cylinder, and if we have our gas in here, we're taking that cylinder and so let's say the piston starts up here. If we decrease that volume, we increase the pressure. It's like having a bike pump. If the bike pump is plugged, pressure can't go anywhere, so you just, as you decrease the volume, push that plunger down, it increases the pressure. If you do the opposite and you pull the plunger up, you increase the volume, so you decrease the pressure. So that was Boyle's law. So when you do this, it will affect the equilibrium. If there's a different number of gas molecules in the products relative to the reactants. So I'm going to write this larger. So this is the reaction we're looking at here. These are all gases. So if we decrease the volume of this cylinder, that's increasing the pressure. So if we increase the pressure, this reaction is going to want to shift to the side that has the fewest number of gas molecules. Because if we can take a if we can take multiple gas molecules and combine them together, there's going to be fewer particles in the space. So they'll occupy a smaller amount of space, and it will decrease the pressure. So for this reaction, we have, I guess I didn't need to write it bigger. We have 1 mole of nitrogen. I wrote this wrong. This is H2. That makes more sense. We have 1 mole of nitrogen and 3 moles of hydrogen. But if this reaction shifts to the right, we only have 2 moles of ammonia. So we'll take those 4 particles and compress them into just 2. And so that will clear up a lot of space, and the pressure will decrease. So for this reaction, we have more gas on the left, and we have less gas on the right. So increasing pressure will cause this reaction to shift to the right. If we decrease the pressure, so we pull that plunger back up, then it'll shift to the side with more gas because it wants to maintain equilibrium. And so decreasing pressure will shift it to the left. Or exactly what happens here, right? So if we increase the volume by pulling up on the plunger, the reaction will shift to the left to counter that change in the concentration of products relative to reactants. All right. So to summarize this, for volume changes in equilibrium, decreasing the volume causes the reaction to shift in the direction that has fewer moles of gas particles. Increasing the volume will cause the reaction to shift in the direction that has more moles of gas particles. And if the moles of gas particles on both sides of that chemical reaction are the same, then changing volume, changing pressure, won't have any effect. Because both sides of the reaction, the concentration of products and reactants will change the same. And so if the concentrations don't change, the rates of reaction don't change, and equilibrium doesn't shift. Okay, so for this system, we have sulfur dioxide and oxygen reacting to form sulfur trioxide. So if we decrease the volume of this reaction mixture, what does that do to the pressure? Yeah, decreasing volume increases pressure. So if we are increasing the pressure, which side, products or reactants, has fewer moles of gas? The product has, so really you can just add up the coefficients. So here we have 2 on the products, and 2 plus 1 would have 3 in the reactants. So we have more moles of gas in our reactants. So if we increase pressure, we have more moles of reactants, more moles of gas in the reactants. Which way does the reaction shift? Yeah. More gas. Sorry, I should have written some of this down. It's a lot to keep track of. Okay, so yeah, it shifts to the right. So decreasing the volume increases pressure. Reaction shifts right. Okay. So what happens if we increase the volume of the reaction?
Opposite.
The opposite's going to happen because we decrease pressure and then the reaction shifts left. It's a lot, I know. There's a lot of different factors at play here because one thing, it's a domino effect. One thing affects another thing, affects another thing. But if you can wrap your mind around all of those successive steps and keep in mind all those dominoes, that when you, by changing the volume, you create this whole cascade effect of things, that's how you really know it. And you'll be able to apply it to any reaction, and it won't just be based on rote memorization. But there is yet another factor that can change equilibrium. Not as complicated as changing the volume. But for reactions that are either exothermic or endothermic, we can think of that heat as a reactant or product, depending on if it's exothermic or endothermic. So for an exothermic reaction, we can think of the heat as a product. Remember, exothermic means that it's generating or releasing heat. It's like a match, things burning, that's exothermic. So if we raise the temperature of an exothermic reaction, it's like adding more product. And so the reaction will shift to the left. Not necessarily if you're actually burning things, but for other exothermic reactions. In an endothermic reaction, heat is one of the reactants. And so endothermic reactions would feel cold to the touch because they're absorbing heat from their surroundings. So if you raise the temperature for an endothermic reaction, that's like adding heat to the reactant side. So it'll shift the reaction to the right. Adding more of those reactions, you're adding that heat that it's trying to suck up from its surroundings. It's going to form more products. All right, so for our exothermic reaction, if we turn up the temperature, we're adding more heat, the reaction will shift to the left. If we remove heat, cool that reaction down, then the reaction will shift to the right because you're removing some of the product. In an endothermic reaction, it's the opposite, because now heat is one of the reactants. So as you add more heat, you're adding more reactants, and it shifts to the to the right. If you remove heat then from an endothermic reaction, it will shift to the left. There's a cool reaction with dinitrogen tetroxide. This reaction is endothermic, so heat is one of our reactants. And you can change the color of this vial. So this is an ampule, it's a sealed glass tube. If you change the temperature, it changes the color. So it's kind of like, temperature sensitive cups and stuff, right? That shifts the color. So if we heat this up, we're adding more heat, that's going to shift it to the right, and we'll get the brown, warm nitrous oxide, NO2, nitrogen dioxide. If we cool that back down, we're removing heat, which is one of the reactants again, so it'll shift to the left, and we'll get dinitrogen tetroxide, which is blue. Or clear, maybe. Hard to tell. So, summarizing, exothermic heat is a product. And then it's just like changing the concentration of one of your products. Increasing the concentration, increasing the temperature is increasing the heat, so it shifts away from products. Decreasing temperature, you're removing heat, so you're removing one of the products, and it shifts to the right. In endothermic reactions, heat is a reactant, and so increasing the temperature shifts it to the right, away from the reactants, and then decreasing temperature causes it to shift to the left towards the reactants. Okay, so for this reaction, what would be, well, this is an exothermic reaction. So which side is the heat going to be on? Is it a product or a reactant?
Product.
It's a product. So we can add that in there. And now if we increase the temperature, which way does the reaction shift? Slide to the left. And if we decrease the temperature, it goes to the right. What would happen if we increased the pressure? Yeah, decrease volume, increase pressure. Which way would it shift?
Right.
It would shift to the right. Because there are fewer moles of gas in the products than there are in the reactants. Okay, that's Le Chatelier's principle. There's a lot of stuff in this equilibrium chapter because everything exists at an equilibrium. This is not unlike the equilibrium constants. But now we're talking about things dissolving. So a lot of things that we think of as insoluble actually dissolve just a little bit. And you can use the solubility product constant to figure out exactly how much dissolves for something that's only very, very slightly soluble. So as you remember, solids are emitted from equilibrium expressions. But we still write this out. Calcium carbonate. So if we had calcium carbonate, so this is a solid in equilibrium with Ca2 plus CO3 2 minus, and both of these would be aqueous. So we emit the solid, so we leave out our only reactant here, and we include just these ions that would be formed by the tiny amount that does dissolve. So a large KSP means we're shifting towards the reactants, or that we have a lot more reactants than we do product, just like KEQ. So if we have a large KSP, that means the compound is very soluble because you're creating a lot of the ions, which are what you use to calculate KSP. And then if you have a very small KSP, that means you're not producing all those ions, and you have something that's very insoluble or not very soluble. And these are written the same way as the equilibrium constants. So for barium sulfate, which is a solid, any tiny amount that does dissolve would be barium 2 plus and sulfate, SO4 2 minus. So we just have KSP equals the concentration of barium times the concentration of sulfate. And if they had a coefficient, then we would use that in the equation as well. So just like equilibrium constants, they're really just a special case where we have one reactant and it's a solid. Here's a bunch of equilibrium constants. There's some in here like lead sulfide, PBS, not the public broadcast service. Very insoluble, right? Times 10 to the negative 29 of those ions in solution. Other things on here, Still probably you'd consider insoluble because it's a very small number still, but a lot more soluble than lead sulfide. All right, so if we want to write an equilibrium expression for these ionic compounds, or a solubility product constant, the first step would be to write out the ions that it's going to form when it dissolves. So if we have a tiny amount of, and this is, I'm going to make a reminder to myself to change the font so you can tell if it's an I or an L. Capital I, lowercase l. So we'd have silver iodide. And that silver iodide, if it did dissolve, would just produce the ions of silver iodide. So a silver ion, which would be Ag+, plus an iodide, which is I-. We should probably include here, this is solid, this is aqueous, this is aqueous. And when you get that far, now we just write, just like we would for KEQ, but now it's specifically KSP. So this will be the concentration of Ag+ times the concentration of I-. And just as a reminder, brackets equals molarity, concentration in molarity, which is also moles over liter. Never forget. Yeah, so that's it for A. So for calcium hydroxide, we'll write out this expression. What would be the products of calcium hydroxide dissolving? Would be the first one. Yep, calcium, Ca2+, plus what? OH-, but we have two of them, right? So we get two separate ions out of there, so we need to put them in parentheses, the subscript. Okay, and then KSP equals concentration Ca2+ times the concentration of OH-, and then because it has a coefficient of 2, we'll square that. Any questions? So one of the useful things that we can do with this is that we can calculate molar solubility, which is the number of moles of a compound that will dissolve in 1 liter of solvent. So it's calculated from KSP, and it's abbreviated S. And the way that we do this is we write out the KSP equation. So again, here we have silver chloride instead of silver iodide like we had before, but we just have these two ions. So we say, okay, we're going to produce these two ions. And so Ag+ and Cl-. And then we can write in KSP is 1.77 times 10 to the negative 10. And then what we want to know, what S tells us, what molar solubility tells us, molar solubility is the moles of AgCl, in this case, per liter of water that will dissolve. So it's not going to be KSP, because KSP is telling us really the ratio of the ions that are formed to, well, in this case are solid, but we don't include solids in this. So what we do instead is we say, well, both of these ions would be coming from the same source. So for every silver chloride molecule that dissolves, it's going to produce an Ag plus and ACl minus. So you'd say that both of these are coming from the same source. So we're going to substitute both of these for S. You can think of that as, the source if you want. 1.77 times 10 to the negative 10. So S times S is going to be S squared. And so to solve this, it's really the ions that the solid produces raised to the power that is the number of those ions. So to get S by itself instead of S squared, we do like we did before, and this is raised to the 1/2, and this is raised to the 1/2. Or if you're more comfortable with saying square root, we're taking the square root there. It's the same math. So 1.77 times 10 times 10 to the negative 10 raised to the 1/2. So that's 1.3, 1.33 times 10 to the negative 5 equals S. You're not getting the same thing?
I don't think I'm reading correctly, that's why.
Oh, okay. We can take a look at it after. Okay. If you're having the problem with your calculator, yeah, please, let me help you figure it out. Because I would hate to have you lose points because typing it into your calculator wrong. So that's molar solubility. I'm going to have to look up KSP, huh? So if we were to do this for calcium sulfate, again, it's always the easiest to, instead of trying to do, actually, yeah, I'll say this. Don't do anything in your head that you don't have to. If you have to do some math, don't do it in your head. Use the calculator. It's so easy to make mistakes if you're not looking at it. So like for this, write out the sort of the dissolution equation. So if this dissolves, we're going to get Ca2 plus SO4 2 minus, solid, aqueous, and aqueous. So what's our KSP equation going to be? Yep. Concentration of Ca2 plus times the concentration of SO4 2 minus. And then if we want to solve this one, we need calcium sulfate. Calcium sulfate.
Are we going to get this table for the test?
I would just give you the KSP.
It would be kind of lame if we had to write all that on our paper.
No. Very unnecessary. So it's 7.1 times 10 to the negative 5. All right, and if we're doing the same thing again, we replace these with S. And then we'll have S squared equals 7.10 times 10 to the minus 5. So we can take this to the 1/2, or square root. So 7.1 times 10 to the negative 5 raised to the 0.5. And that is going to be, so S equals 8.43 times 10 to the negative 3. Yeah. So that's how many moles of calcium sulfate would dissolve per liter of water. Not very many. Okay. Man, I think this chapter has the most sort of like mode shifts out of any of them, because now we're going to talk about something else. So we talked about some things that affect the rate of reaction. We change the concentration, we'll change the rate of reaction, right? Higher concentration of products will increase that rate. You can also increase the temperature. So if you add more energy to the system, then you have more collisions that exist with enough energy. One of the other things we can do is use a catalyst, because that amount of energy that's required for that reaction to happen is called the activation energy. So there's essentially this energy barrier, right? You have to have enough energy to get over that barrier, and then the reaction can happen. At a fundamental level, this happens because for most chemical reactions, you have to break. The original bonds must begin to break before you can make new bonds. So if this is our reaction pathway, you think of the origin here as where nothing has happened, and then the ending over here is where we get our products. So for any given temperature, higher the activation energy for a chemical reaction, the slower reaction rate. So if the difference between energy of the reactants and the activation energy gets larger, it's a larger barrier to overcome before you can roll down the hill on the other side to get to the products. Because most reactions happen because the energy of the reactants is higher than the energy of the products. And just like water wants to flow downhill, everything's trying to get to the lowest energy state possible. Okay, so I got ahead of myself just a little bit. But these are the ways we talked about to increase the reaction rate. If we increase the concentration, then we have more molecules. And if we have more molecules, there's a higher chance that some of them will collide with enough energy to get over this barrier. If we have fewer particles, then there's a smaller chance that one of those collisions will have that energy. Again, we can increase the temperature. So if we take the energy of the reactants, essentially, add more energy in the form of heat, then they get closer to that energy barrier. You have more things hitting and getting over. Or we can use a catalyst. A catalyst is kind of like, instead of trying to get over the hill, you're drilling a tunnel through the hill. So why use all this extra energy? The catalyst lowers that energy barrier and says, hey, you can take this path instead that requires a lot less energy. So you can speed up a reaction without increasing the concentration or increasing the temperature. So, again, if we think about this like a hill, we can increase the reaction rate by pushing harder, which would be like increasing the temperature, and kind of like increasing the reaction rate. You have more things trying to push up this hill, more chance that they have the energy. But a catalyst finds a path that goes around the hill, or I like to think of it like a tunnel through the hill. So you can skip all of that. So that alternate pathway has a lower activation energy. This is mostly important. I think we're going to get into the why of this now. Yeah. Mostly important because there's a lot of things that are thermally sensitive. So say you've got some industrial process, you're making, I should have had something. Drawing blanks. So you're trying to make something and you can't heat it up because it would destroy it. Right? So if you can't heat it up, but you need to speed up this reaction, and maybe one of your reactants is really expensive, so you don't want to just use a lot of reactant, you're going to want a catalyst to make that process happen faster instead. And the human body, and actually all living organisms, use enzymes, which are specialized catalysts. Oftentimes, they take molecules and they hold them in a special position that makes them more vulnerable to reaction. Or they'll grab two separate molecules and smash them together to cause a reaction to happen. This is why, this is why insulin should be cheap, because we've engineered E. coli to make insulin. It's not supposed to, but we've genetically modified it. You grow it in a vat, and then it uses enzymes to make insulin in huge quantities for very, very little money. So this is how life happens, though. You need these enzymes because the reactions otherwise would happen too slowly. We'd all just be trees. So the enzyme sucrase is a catalyst, creates a pathway with lower activation energy. We talked about that. This is the cool thing, though. So when sucrose gets into the activation site of this enzyme, it strains that bond, actually like physically strains the bond by holding it in a position where it's easier to break that bond. So you can split sucrose into glucose and fructose units more easily. Would you look at that? 6:15 and we finished chapter 15. Awesome. So it means we only have chapter 17 left. How long is chapter 17? All right, we'll talk about radioactivity next time. It's all very interesting, but